Assalamualaikum to our lecturer, technologist Dr. Zulkifli bin Ibrahim. We are here to present our technical investigation on the analysis of power flow and short circuit study for course BLK3933. Our YouTube presentation link is provided on the title slide later. Our team consists of 4 members. I am Ahmad Zaim bin Aidi Zubaidi. My matrix number is P11251028. I will be covering for the first section our presentation. Power system network topology. For our model, we implemented an IEEE 5-bus system based on the technical report by Ashwin Prasad. The infrastructure include 2 generator units at bus 1 and bus 2 to meet the system power requirement, a mesh topology consisting of 7 transmission lines for redundancy, and 3 load centers at bus 3, 4 and 5. We define our parameter in power world as follows. Bus 1 is the slack or swing bus acting as our reference node with a voltage of 1.0 per unit and 0 degree phase angle. Then bus 2 is our PV bus, which is voltage controlled. For bus 3, 4 and 5 are PQ buses where the real and reactive power remain constant. All modeling was executed using Power World Simulator to ensure accurate visualization of the power system flow. This is our single line diagram of the 5-bus system according to IEEE report. This is our SLD input data. For the table 1 is given to line data, 5-bus system. It gives a line to line and the line impedance in reactance NPU and resistance NPU. Then the line charging substance B over 2 per unit. Then for the table 2, bus data for 5-bus system. It gives it's showing the voltage setting in bus 1 equal to 1.04 per unit, then bus 2 1.02 per unit, and other load requirement. Now I will pass the next section for my members.
Hi, thank you for my previous member. So my name is Suresh. My metric number is B1124102111. So I will explain about power flow and short circuit analysis. So there are several types of fault analysis that we have learned, which is single line to ground, line to line, double line to line, and three phase balanced. The result of fault analysis that will be attached is based on bus 3 only. So this is our single line to ground. So the first one is I will explain about fault location, our bus our bus 3. So fault type is as shown as in the picture. It is single line to ground. So there are many kinds of value we have get through this. That is for phase volt A, volt B, phase volt C, phase angle A, and phase angle B and C. So uh, our fault current scale current by is 1.0, and magnitude is 1.043, and scale mag is 1.048, and angle is negative 72.96. And our submarine phase current, that is A, for A is 1.843, and the degree angle is negative 72.96 degree, and for B is our PU is 0, and our degree is 81.54 degree, and C is same as B. So that's all. So this is the line to line voltage magnitude. So for a fault between phase B and at phase B and C at bus 3. So voltages on two faulted phase B and C drop equally as they are shorted together. The voltage on the healthy phase A remains largely unchanged at 1.0 pu. These types of fault does not involve the ground, so zero sequence currents are absent. The voltage imbalance informs the settings for negative sequence voltage release. So here's the double line to ground fault, that is voltage magnitude. So a double line to ground fault, phases B and C to ground, presents a more complex voltage profile. The voltages on two faulted phases collapse to near zero. The healthy phase A voltage may actually increase above nominal depending on system grounding. This server voltage set across two phases can trip sensitive industrial loads and requires fast-acting protection. This is three-phase balance, that is for voltage magnitude. So a three-phase voltage fault at bus 3 represents the most severe but symmetrical disturbance. This graph shows that voltages at the fault location drop to zero on all three phases. Voltages at remote buses will also sag significantly depending on the system impedance. This simulation is the primary input for transition stability studies and determines the maximum short circuit current for breaker duty calculations.
Nama saya Muhammad Faiz bin Amiruddin. Nombor metrik saya B1124101770. Dan pada hari ini saya akan menunjukkan simulation untuk litar kami yang telah siap ini. Kami follow apa yang ada di dalam report dan inilah hasilnya. Seperti yang boleh dilihat, nilai-nilai yang akan keluar saya letak di sebelah setiap komponen masing-masing untuk memudahkan resultnya untuk dilihat. So saya terus ke run mode dan run. Okay, seperti yang boleh dilihat, litar tiada masalah untuk run. Semuanya berjalan dengan lancar dan nilai-nilainya pun sama macam apa yang ada di dalam report. So kita terus ke fault analysis. Okay. Untuk fault analysis, kami hanya menunjukkan result untuk bus ketiga sahaja. Okay, single line to ground dulu. Kita tekan calculate. Nilai akan keluar. Line to line. Calculate. Nilai akan keluar. Three phase balance. Calculate. Nilai akan keluar. Dan juga yang terakhir, double line to ground. Calculate dan nilai akan keluar juga. So seterusnya kita tengok di line. Tekan calculate, akan keluar. Line to line. Three phase balance. Dan double line to ground. So saya rasa setakat itu sahaja daripada saya. Sekian, terima kasih.
Hello, my name is Pritish Nayanarakandan and my metric number is B1124100201. So now that we have covered our technical modeling, let's look at the legal and regulatory framework that governs our design to ensure it meets Malaysian standards. So our primary reference for this simulation is the TNB Electricity Supply Application Handbook, ASA version 3.1. Every result we have generated has been cross-referenced against this guideline to ensure industry standard accuracy. So the next one is a short circuit policy. A critical part of our safety verification is the short circuit rating policy. For a 130 kV, 132 kV system, uh, the design must be robust enough to withstand a fault current of 31.5 K for 3 seconds. Similarly, for our 11 kV system, we have ensured compliance with the 20 K for 3 second requirement. And the next one is statutory compliance. Beyond technical manuals, our design adheres strictly to the Electricity Supply Act 1990 and Electricity Regulation 1994. These are the legal pillars for the electrical safety in Malaysia. And lastly, by verifying this fault level L plus 2, we can confidently state that our stimulated system isn't just a theoretically correct, it is a legally compliant and safe for the deployment. But engineering isn't just about laws and numbers. It's about the people who rely on this power every day. So the first one is a societal foundation. Mm, Reliability is the foundation of a modern society. A stable power flow is the lifeblood of our infrastructure, supporting everything from high-tech industries to life-saving equipment to in hospitals and our education system. So the next one is the impact of a failure. By performing accurate load flow analysis, we are effectively preventing blackouts to ensure social stability and keep our economy productive, as even a few minutes of power loss can result in massive industrial setbacks. And the next one is ethical values. We have also adopted TNB's core value of caring. To us, caring means providing a safe and dependable energy supply. We uphold our professional integrity by prioritizing human safety through rigorous short circuit calculation. And the last one is the cultural consideration. Finally, from a cultural perspective, reliable electricity improves the overall standards of living. It allows our community to carry out cultural activities and daily tradition without fear of disruption. In conclusion, our remodeling of the IEEE 5-bus system using the Powell has successfully demonstrated the system performance under both steady state and fault condition. Our result proves that this system is technically sound, legally compliant, and compliant with the Malaysian regulation, and most importantly, reliable for societal needs. Thank you for your attention.